This is question 2 from the Leaving Cert Higher Level Paper 1 from 2020. Up the top right, you'll find a card that will bring you to the playlist that has all the solutions to the questions in this paper. And below the video, you'll find a link to an image of this question, so you can try it before looking at this solution. In part A of this question, they give us these two equations with Z1 and Z2 being the unknowns. They tell us they're complex numbers, and they ask us to find both of those complex numbers in the form of A plus BI. So how we go about this is we assign Z1 as two numbers, a real and an imaginary number. I'll just go, it's a bit confusing because they used A and B. No, I'll use it anyway. I'll use A plus BI. Just any letters you want really, any variables you want. X and Y is fine as well, but I am going to use more of them, so I usually start with A. So Z2, I'll then go C plus a D. So we want to find out basically these four variables are. Rather than trying to find out what these two variables, Z1 and Z2 are, we'll look for each of these individually. That's sort of how we go about most of these questions. So you'll see what I mean when we do the first line here. Because complex numbers actually have two bits of information inside it. They're complex, they hold two bits of information. If I write out this first line again, instead of Z1, I'm going to write my new broken up part. So A plus a BI equals minus 4 plus 3I. If you multiply this in, I times BI, you'll get I squared. B times I squared. I squared is minus 1, so you get minus B out of that one. That's the real part. And an imaginary bit, you'll get I times A. You'll get AI. And that'll equal minus 4 plus 3I. Now for complex numbers, we can say all the real numbers on the left equal all the real numbers on the right. So instead of this being one equation, we could write two different things. All the reals, minus B is the only real, must equal minus 4. And also all the imaginary, A, or AI, but I can leave all the I's out if I want. Parts of all the imaginary, A is equal to 3. I could have wrote AI is equal to 3I and then just divided by I. That's where I'm getting that. So I've actually found A and B already. B is 4. B is equal to plus 4. So I can rewrite Z1 is equal to 3 plus 4I. And we continue on with the next line. I'll write this one out. You won't always get the answer from one line. I might have been left with some unknowns here and I would have had to solve a simultaneous equation. But in this case it was easy enough. The first line could answer the first one. And now the second one will answer the second one. So 3 times Z1, instead of Z1, let's write in what we now know it to be. 3 plus 4I. Minus, instead of Z2, we'll put in the letters we made up. That's minus C minus DI. I've multiplied by a minus 1, so make sure to multiply both of them by minus. And that's equal to 11 plus 17I. We'll do this one a bit faster. What we're looking for is all the real numbers on the left. Let's see, where will we get reals? 3 times 3, that'll be a real number, 9. 3 times, that'll be an imaginary number. Minus C, that's a real number, equals 11. And if we rearrange this, we get minus C is equal to 2 and C is equal to minus 2. Then if we get the imaginary parts, let's see, 3 times 4I, that'll give us 12 I's. Minus DI, so minus D, is equal to 17I, equal to 17. So if we rearrange this again, we get minus D is equal to 5, or D is equal to minus 5. So that means Z2 is minus 2 minus 5I. And that's the answer to part A. That's both Z1 and Z2 in the form of A plus BI. They also tell us they're integers. So, well, we don't know if we're right, but at least we didn't get decimals or fractions or anything like that. So we're quite confident. There's one answer and there's the other. Right, that's part A. I'll need more room for part B, so let me rub this out and we'll do part B. In part B, they tell us these two, and it's only two numbers here, two complex numbers, are the first two numbers of a geometric sequence. And they want us to find the common ratio between them. So this is the first number, the second number, there will be a third, a fourth, a fifth, and part 2 of this question wants us to find out what the ninth number is, in fact. So just like any other geometric sequence, let's see, 2, 4, 8, 16, there's a common ratio. And geometric, we have multiplication is important here. So something multiplies by the first one to get the second. Something multiplies by the second to get the third. In this case, it's easy, see, it's 2. But something's multiplying by this one to get this one. I guess there's 2 ways to do this. The simplest would be to divide any number divided by the one in front of it. So in this case, 5 minus I divided by 3 plus 2I. By the way, another way to do this question would be, I won't finish it, but it'd be take the first number, multiply it by a blank number. That's what I call it, at least, A plus BI, and that equals 5 minus I. That's it's a lot of people rather this way. It's quite a quick way. You'll find A and B. You'll find what this missing number is. Whereas you'll get the same way by doing it here. To divide complex numbers, we take the bottom row and use the conjugate of it. Sorry, that should be 3 minus 2i. 3 minus 2i. So we're using this number because it cancels the bottom out quite nicely. And we can multiply anything by 1, because that's all this is. It's 1. Something divided by the same thing. It's just 1. So if we do this, let me get all the real numbers on top. We'll get 3 by 5, that'll be 15. We'll get I by minus I by minus 2i will be 2i squared, which will turn into minus 2. Right, all the complex numbers on top, we'll get minus 3i. And we'll get minus 10i. On the bottom row, conjugates multiply quite easily. It's just the first terms multiply is 9. And it's the second ones. 2i multiplied by 2i is 4i squared, or sorry, minus 4i squared in this case. And the I squared is a minus 1, so we get plus 4. And the other terms cancel. 3 times minus 2i is minus 6i. 3 times 2i is plus 6i. They cancel. So we just need to clean this one up. We get 13 minus 13i divided by 13. Works out quite neatly for us. That goes in 1, that goes in 1. And we get 1 minus I. You would have got the same number here if you did it this way. So that's part 1. We get the common ratio. So this is what must have multiplied this to get here. For part 2, they tell us to use the Marx Theorem to find out what the ninth term is. Now I'm guessing students got a bit confused by this because the Marx Theorem doesn't help you find the ninth term. You still need to look up how to get the ninth term of a sequence. And that's Tn is equal to A multiplied by or to the power of n minus 1. So you still needed to use this. The Marx Theorem is just actually going to help you with this part of the sum. So to clean this up, we get, to get the ninth term, T9, would be equal to A, the first term, that's 3 plus 2i, or the common ratio, we just found that, let me put or in there, and that's 1 minus I to the power of 9 minus 1, that's 8. So to use the Marx Theorem helps us solve complex numbers to the powers of. So to do that, we really need to change this. Well, you know what, let me write the Marx Theorem out up here. It is or multiplied by cosine theta plus I sine theta, all of this to the power of n. That is equal to or to the power of n multiplied by cosine n theta, not just theta, n theta, plus I sine n theta. That's the Marx Theorem. Now again, well, hopefully you've seen the Marx Theorem before, so you're not too confused. But this doesn't look anything like this. That's because this is in standard form and this is in polar form. So that's the first thing. We need to change 1 plus I into polar form. To do that, so that'll be in some form like or and cosine theta. So really we need to know what is or and what is theta. To do that, I like to explain how to do it at least by drawing a picture, an argon diagram. And that is, okay, so 1 minus I, that looks like this. There's 1, there's minus I. It looks like this. That's where that point is. To get it in polar form, instead of just knowing the x and the y to find a point, there's another way. We could know the angle something makes. The angle something points. In this case, it points down with this angle, and the length it goes from it. So that's what polar form is. So really, I need to know the length of this and the angle of this. And that's easy enough to find, because really we're dealing with a triangle here. That's 1 length, that's 1. It's 1 height. So I actually don't need to do any maths to find this. It's just 45 degrees. It's quite easy to find. Or you could have got the tangent of this divided by this. Would have found it as well. And we need to know the length of this. That's Pythagoras theorem. So 1 squared plus 1 squared is 2. And we get the square root of that. So this in polar form would be square root of 2. It's the or part. Multiplied by cosine 45 plus I, sorry, this should be minus 45. We're going down here. 45 is up this way. This is minus 45. Or you could call it 315. If you rather, 315 is the same as minus 45 in angles. Okay, sine minus 45. Very important, those minuses. They actually won't change the answer in this as it happens. So that's this written in polar form. To save me writing out another line, you should probably write another line here. I'm going to be able to cheat and just put in to the power of 8. Put in to the power of 8. Now this is where I'm using the Moivre's theorem. This is why they told us, use the Moivre's theorem here. They wanted to give you a hint to go down this path. So the Moivre's theorem is quite straightforward with something like this. We get or to the power of 8. It's this guy to the power of 8. Square root of 2 is 2 to the power of a half, so that to the power of 8. And then we get cosine 8 multiplied by minus 45. Double check on a calculator, but it's minus 360. Plus I sine minus 360. Let's see, 2 to the power of a half is 8 multiplied by a half is 4. 2 to the power of 4 is 16. Double check with a calculator if you're not sure though. It's 16. Now cosine minus 360. Let's see, 360 minus, we go down. We get all the way back to the start. 0. It's the same as 0. Cosines and sines, they repeat every 360. So this is the same as plus 360. It's the same as 0. It's the same as 720. Cosine of 0 is 1. And plus I multiplied by sine 0, or this, is 0. So that's gone. That's all gone. We're just left with 1 times 60. 60. So I'll jump back into this line. Again, you should probably write this under this one, but I'll jump back onto this line. So this is just the same as 3 plus 2i multiplied by 16. Or I'll write 16 in front. 16 times 3 is, let's see, 30 plus 24 is 54. Plus 16 times 2 is 32. 32i. So that is the ninth term of this sequence. And we did that using the equation for sequences. We got the ninth term, and really what we needed the Moivre's theorem was to get the power of a complex number, to get the power of 8 of a complex number. There was one more way to do this question, which I'm guessing a few students probably did, and it's okay to, actually it's not okay to do it because the question told you to use the Moivre's theorem. That's probably why they said that, to weed out those people. Because you could have just multiplied this by, I've rubbed it out now, by this or term here, and done that another 7 times after this. This is already done once. Yeah, do it again, another 8 times after this. And you would have got the same answers here, but I guess they would have taken marks away because you did not use the Moivre's theorem. So I was going to say there's another way to do it. There's not. You need to do that. Alright, that's that question. If you have any follow-up questions about it, please put them in the comments below. I'll do my best to answer. Or if you see any mistakes, let me know and I'll try and fix them. Thanks for watching. Have a great day.